The Heisenberg uncertainty principle says that we can never know simultaneously the velocity and the position of an electron at any given time. If we try to determine one, the other one becomes undeterminable. What are the consequences of the Heisenberg uncertainty principle? When we try to pinpoint where the electron is, it ends up being anywhere else except where we think it is. That means that the electrons couldn't be trapped in fixed energy levels like the Bohr model would suggest. If the Bohr model were the setup, the electron would collapse in on the nucleus. A wave function is an equation that describes where one might find an electron in an atom. An orbital is a probability function to show where an electron might be found. Because we said that electrons can't be found at any specific spot, if we say that they're at a certain spot, then they're anywhere else except that, we get this idea of an orbital. And so somebody calculated the probability of where the electron might be. The shapes that we see are actually a mixture of places where there's high electron density, called a lobe, and places where there is low electron density or no electron density, called a node. If I look at this and I were to draw a circle around where most of the electrons are, that would give us the shape that we'll see in a later slide of an s orbital. And if I were to look at this one, if I were to circle where the electrons are likely to be found, this would give me a p orbital, as we will see in the next slides. There are four common orbitals that we are going to be looking at. The first one is an s orbital. I want to define what the shape of an s orbital is. An s orbital has this spherical shape to it that you see below. How many orientations are there for an s orbital? There's only one way to orient an s orbital in space because it is a sphere. And how many electrons can an s orbital hold? We will confirm later on that there are 2 electrons that can be held in any s orbital. The second type of orbital is a p orbital. What is the shape of a p orbital? And you should be able to draw the shape later. The shape of the p orbital is a dumbbell shape. How many orientations are there for a p orbital? Now there is a node in the middle of this, and because of that you can actually orient this on 3 different axes, the x-axis, the y-axis, or the z-axis, and so we get 3 different orientations. In any energy level, how many total electrons can a group of p orbitals hold? Each of these, as we'll find out, can hold 2 electrons, and so if we add up all of those electrons, we would find out that there are 6 electrons total in a group of p orbitals. D orbitals have an even more interesting shape. In this case, they now have 2 different nodes that cut the orbital in half and then in half again. And so there are 5 different orientations, and some of them have unique shapes. One of them does have this unique shape. They refer to it as the donut hole, and then there is an orbital going above and below that donut hole. Again, each of these can hold 2 electrons, and so in any energy level, a group of d orbitals can hold 10 electrons. The f orbitals begin to become really bizarre because they're being split in half and then split in half again and then split in half a third time because of how many nodes there are. If you can draw them, then spectacular, but I'm not going to ask you to draw them. I would ask you to identify them. There are 7 different orientations for an f orbital, and again, if we can put 2 electrons into each of those orientations, we get that there would be 14 electrons that could be held in a group of f orbitals. There are 4 quantum numbers that describe the electrons. You can kind of think of this as being the address for an electron. Right now I'm just going to define them, and then in later slides we will take a look at how these numbers are calculated. The first quantum number is n, and that can be any integer, so any whole number from 1 to infinity. The second one is L, and that is that for any n value, the L value can be n minus 1 and any integer down to 0. So again, any whole number. The third quantum number is referred to as m sub L, and that can be from negative L to positive L and any integers in between. The fourth quantum number is m sub s, and that can be either a positive 1/2 or a negative 1/2 for every m sub L value. The first quantum number is called the primary quantum number, and it is given the symbol lowercase n. That relates to the energy level that was shown in the Bohr model. What values can n be? N can be any integer from 1 to infinity. And so this could be that n is equal to 1, it could be equal to 2, it could be 3, 4, 5, 6, and so on. The highest number that we're generally going to see for an n value is 7. The second quantum number is referred to as the secondary or angular momentum quantum number, and it's given the symbol L. What values can L be? For any n value, L can be any n minus 1 and any integer down to 0. So if I chose n is equal to 5, L could be n minus 1, so 5 minus 1 is 4, but it could also be 3, 2, 1, or 0. We will find out that it doesn't have to be all of those values, that it can be a specific one of these L values. And what I mean by that is that each orbital actually relates to an L value. And so for an s orbital actually has an L value equal to 0. So if I say something is an s orbital, it has an L value of 0. An L value of 1 correlates to a p orbital. An L value of 2 correlates to a d orbital. And an L value of 3 correlates to an f orbital. In the n equals 2 level, what types of orbitals can exist? If n equals 2, that means that L can be 1 or it can be 0. And so what that indicates is that if L equals 1, that's a p orbital, and if L equals 0, that's an s orbital. So this indicates that in level 2 there is only a 2s and a 2p orbital. There is no 2d or 2f orbital because the quantum numbers will not allow it. The magnetic quantum number is given the symbol m sub L. What values can m sub L be? M sub L can be negative L to positive L and any integers in between. If L is 4, then m sub L could be negative 4 to positive 4, and any integer in between, which would be negative 3, negative 2, negative 1, 0, 1, 2, 3, and 4. The L values and m sub L values can be used to determine how many different orientations can exist. So let's take a look at an example. When L equals 2, what values of m sub L can exist? M sub L is defined as negative L to positive L and any integer in between. And so negative 2, negative 1, 0, 1, and 2 could all exist as possible m sub L values. What type of orbital correlates to L equals 2? That would be a d orbital. That just comes from the definition that L equals 2 correlates with d. And so what this indicates is that for d orbitals, if we count up how many different m sub L values there are 5 different m sub L values, and so that means that there are 5 different orientations for a d orbital. which confirms what we saw earlier. The fourth quantum number is not completely related to the other three. It's called the electron spin quantum number, and it's given the symbol m sub s. What values can m sub s be? M sub s can be plus 1/2 or minus 1/2 for every m sub l value. That essentially means that if you have an m sub l, let's say I just say m sub l is equal to -5, that there can be two possible electrons in that, one of them having a plus 1/2 spin and the other having a negative 1/2 spin. What is the total number of electrons that can be found in a 3p orbital? Let's think about what the values of n and l are. It's a 3p orbital, and so that means that n is equal to 3. Now, you could say L is going to be equal to 2, 1, or 0, but the moment that you say it's a p orbital, you eliminate all of the options except for 1. And in this case, the L value is going to be 1 because 2 is a d orbital, 1 is a p orbital, and a 0 is an s orbital. So these two options, the d and the s orbital, are eliminated. And so n equals 3, but L is going to equal 1 specifically. Then what we can do is we could say that m sub L is going to be -1, 0, or +1. And the rule after that says that for each of these there can be an m sub s of either plus 1/2 or minus 1/2. And so what that tells us is that for each orientation, and there are 3 orientations, that we could put 2 electrons into each of those orientations. And so again, if I add up how many m sub s values I write down, that indicates that there would be 6 electrons that could be found in a group of 3p orbitals. Is the following combinations of quantum numbers allowed? If not, show 2 ways to correct it. For this one, if n equals 5, L could be 4, 3, 2, 1, or 0. And since L is one of those options, that's an acceptable answer. We're now saying that L is equal to 1, and so that means that for L equals 1, m sub L could be -1, 0, or 1. So the fact that m sub L is a -2 would not be correct, and so this is not a possible set of quantum numbers for an electron. One way that we could fix it is we could say that m sub L equals -1 or 0 or a +1. Or we could, since I didn't put any limitations on what you could do, we could say that L equals 2, and if L equals 2, then m sub L could equal -2. Degenerate means that 2 or more orbitals, in this case, have the same energy. For example, the 3 p orbitals that would be in any level are going to be degenerate. They would all have the same energy. Similarly, the 5d orbitals that are in any level would also be degenerate, as each of the 5 orbitals would have the same energy. We are going to write electron configurations, and there are a few rules and guidelines that will help us. The first guideline or rule states that electrons will reside in the lowest possible energy orbital available. That means that level 1 will get filled before level 2, and level 2 will be filled before level 3. Each orbital can accommodate a maximum of 2 electrons, though sometimes we will think about groups of orbitals where we could have 2 electrons, a maximum of 6 electrons, a maximum of 10 electrons, or a maximum of 14, depending on what type of orbital it is. Electrons will not pair in degenerate orbitals if an empty orbital is available. And what that means is that if we have orbitals that are all at the same energy, they will each fill the orbital half filled before they start pairing up. And then the ordering of the orbitals is predictable for parts of the periodic table. And so the periodic table can be a useful tool for remembering the order that orbitals fill. When we're filling orbitals, as I mentioned, we can use the periodic table. And the way that the periodic table is set up is that there is a group of 2 electrons on the far left. If you kind of take a look and see that the box will have 2 electrons. And so what you'll notice about that is s orbitals can only hold 2 electrons maximum. And so that side is the s block. The middle block, if we count it across, has 10 electrons in it. And so that would be a d block. There on the right side of the periodic table is a block, and if you count it across, you'd find out that there are 6 electrons in that block, and so that block would be a p block. And finally, shown as a drop down from the periodic table is the f block, which contains 14 elements in a row, correlating to 14 electrons that an f orbital can hold. The other thing that we should point out is that the number of the period on the left here will tell you generally what number to write down in front of the orbital. Notice, for example, how in period 2 that you would write a 2s orbital and a 2p orbital, and in period 3 you'd write 3s and 3p. There is a quirk that happens when you get to the d orbitals. You'll notice that we're in period 4, but that the d orbital is 3d. What you do is you take the n value, the period value, and you subtract 1 from it. And similarly, the 6s then leads to 4f. And so what we need to realize is that if you want to find out what the number is in front of the f orbital, that you actually have to take the period number and subtract 2 from it. There are 3 types of configurations that we're going to write. The first one is called the longhand configuration, and this includes all of the orbitals and all of the electrons. The electron orbital diagram breaks down the orbitals, the p, d, and f especially, into suborbitals and draws how many electrons are in each of those. The third kind of configuration is called the shorthand configuration, or sometimes the noble gas configuration. And what it is it's the configuration that shortens everything by writing down the noble gas that comes before the element of interest, and then we write down only those electrons that come after the noble gas. Let's write the 3 different configurations for 2 different elements, oxygen and nickel. For oxygen, there are 8 electrons, and so we want to think about how we can explain where the 8 electrons are in oxygen. The first orbital that's available in every element is the 1s orbital, and an s orbital can only hold 2 electrons in it, so we're going to write a 1s2 there. For the next orbital, if we go to the next level, there's a 2s orbital that's available, and that also can hold 2 electrons. So if we add up the 2 and the 2, we get that explains where 4 electrons are. We need 4 more electrons. The next orbital available is a 2p orbital, and a p orbital can hold up to 6 electrons. If I wrote 6 down, I would have 2 plus 2 plus 6, which is 10. That's more electrons than oxygen has, so I'm only going to write down a 4. For the orbital diagram, let's write down what we would do is we'd say that there's a 1s orbital, and a 1s orbital can hold 2 electrons in it. So I'm going to draw an arrow, one going up and one going down. I'm going to draw a 2s orbital and draw 2 electrons in that. And then for the 2p, in this case, a p orbital can break down into 3 separate orbitals, a d orbital can break down into 5 separate orbitals, and an f can break down into 7. And so for 2p, what we'd actually want to draw is 3 separate orbitals, because each of them can hold 2 electrons. And the rule states that we don't pair electrons up unless we're forced to. We actually separate electrons first. And so what that would look like is we would put an electron in each of the orbitals, and then we would put a fourth electron pointing down. The shorthand would be to look at the noble gas that comes before oxygen, and the noble gas that comes before oxygen is helium. Now, helium has 2 electrons in it, and so that would explain the 1s2 orbital. And so what we'd have to do is we'd have to write everything that came down after helium, and after helium we would have the 2s2 and the 2p4 orbital available and being used. For nickel, the longhand configuration is going to start off very similar. There's a 1s2 orbital, that's the first orbital that's always used and available. And then there's a 2s2 orbital, that's 4 electrons. Nickel has 28 electrons, so we're going to find room for 28 electrons. The next orbital is a 2p orbital, and p orbitals can hold up to 6 electrons. In this case, we want to get to 28 electrons, so we are going to use all 6 spaces. So that now gives us 10 electrons. We're then going to go to level 3. Level 3 is the first kind of orbital available would be a 3s orbital. There are 2 electrons in there. The next orbital available is a 3p, but that will have 6. If I add that up right now, I have 18 electrons. I need to find space for 10 more electrons. The one confusing thing is that the next orbital that is going to be used is actually going to be a 4s orbital. We'll see why that can be a confusing thing, but that's just what comes next in the ordering, and that can hold 2 electrons. Because after that, what you'll remember if you look at the previous slide is that the d orbitals actually had a value of 1 less than what period they were in. And so what it is that the d orbital, the 3d orbital, is actually the next thing. Right now we have 20 electrons in terms of what we've already written down, and so I think I only need 8 more to get to 28. D orbitals can hold a maximum of 10, and so that would be the configuration for nickel. What I'm going to do next is write down the shorthand for nickel, because we can write down the orbital diagram in a shorthand version. So the noble gas that comes before nickel is argon, and argon has 18 electrons. And so if I think about it, the 18 electrons are going to be the 1s2, 2s2, 2p6, 3s2, 3p6 electrons. And so all that would be remaining is the 4s2 and the 3d8 electrons. And then what I can do is I can write down only these electrons in my orbital diagram. So I'm going to write down a 4s that is holding 2 electrons, and then I'm going to write down 5 spaces for d, because d can have 5 different orientations, and I'm going to fill in each of them with an electron first. I want to fill it up with 8 electrons, so I'll split 5 apart, and then number 6, 7, and 8 will pair up. There are 3 different types of magnetism that we can explain based on these electron configurations, or at least 2. The first is paramagnetism, and this is where a substance is weakly magnetic due to unpaired electrons in the electron configuration. Diamagnetic is where a substance is not magnetic because all of the electrons are paired. Those 2 can be explained by writing electron configurations. The third category is ferromagnetism, and this is a substance that is permanently magnetic due to unpaired electrons that are oriented in a specific way. This obviously can sometimes be undone by heating up a magnet of this type, but again, it's something that is specific. And so ferromagnetism is only seen in a few elements. Iron, cobalt, and nickel are 3 examples, and then some of the rare earth metals that are in the lanthanide series are also ferromagnetic. Those are things that if we wanted to know, we would have to look up or memorize. Which of the following elements would have 2 unpaired electrons, and which of the following elements would be diamagnetic? What we need to do is we need to write down the shorthand configuration for each of these, and we need to write down the electron orbital diagrams. One of the mistakes people make, especially on exams, is that they don't write down the orbital diagrams and they try to figure out whether there are unpaired electrons or whether something's diamagnetic, and it doesn't work very well. I will also point out that in this case, it says nickel 63, 64 zinc, 70 germanium, and bromine 73. The numbers after these are telling you something else besides electrons, and so those don't particularly matter to us. So let's start by taking a look and saying nickel. We already wrote the shorthand configuration for nickel. That had the configuration 4s2, and then there are 5 spaces, 3d8, and so that would be 1, 2, 3, that configuration right there. If we look at it, what we'll notice is that there are 2 unpaired electrons, and so that would be an answer to that. It does have unpaired electrons, and so that would be paramagnetic, according to our definition. It is also ferromagnetic, but as I mentioned, I'm not going to expect you to know that part. For zinc, zinc has 30 electrons, so zinc is similar to nickel. These are both related to the element argon, or that's their noble gas that comes before. Zinc would have 4s2 as its configuration, and then instead of 3d8, it would be, there are 10 electrons there, so I'm just going to fill in all 10 spaces. So that would be 4s2 3d10. And in this case, none of the electrons are unpaired, so that's not an answer to the first part. But since all of the electrons are paired, this would be a diamagnetic molecule or atom. Germanium is going to have 32 electrons. There we go, 32 electrons. So that would be the configuration 4s2, 3d. It's related to argon again. That's going to be full with 10 electrons because it would be 3d10, and then it would be 4p with 3 spaces, and I think to get to that we now need to add 2 electrons there. And so that would have 2 unpaired electrons also. Every once in a while somebody will look at this empty spot and think that that's unpaired. It's not unpaired, it's just unfilled. So we don't count that as anything. Because there are unpaired electrons, that would be paramagnetic. Bromine has 35 electrons, and so if we kind of just keep building up, all of these you're noticing have the same sort of setup here. 4s2, 3d10. Now we would go and we would add 3 more electrons compared to what the, so that would be 5 electrons in this bromine, and so that's the 4p group right there. And so for bromine there would be 1 unpaired electron, and since there's 1 unpaired electron, it would be paramagnetic. So the answer to the question is that there are 2 elements that have 2 unpaired electrons, the nickel and the germanium, and then the diamagnetic would be the zinc. For the following set of quantum numbers, identify what type of orbital, 5p, 6d, etc., would be described, and also identify an element that would be using that specific orbital for one of its outermost electrons. The values given here are that n equals 3, L equals 2, and m sub L equals 0. The n equals 3 indicates that it's going to be something with a 3 out in front of it, so it kind of indicates that it's either going to be 3s, 3d, or 3p to begin with. The L equals 2 indicates the type of orbital, and it indicates that it's a d orbital. How do we know? Because L equals 2 is defined as a d orbital, so we would say that this is a 3d orbital, and so it would be specifically this block in the middle here. The M sub L does not actually indicate what electron or what element it is. It just indicates that there is an orbital that has an electron that has M sub L equals 0. And so for this case, what we could do is we could say that everything from scandium, which is the first element in that 3D block, all the way to zinc, any of those could be written down as examples of elements that would be using those electrons in their outermost orbitals. How many electrons in germanium will have the quantum number n equals 4? For this type of question, it will actually help to write down the full, complete electron configuration, because we can then identify what electrons have n equals 4 as their quantum number and what have L equals 2 as their quantum numbers. So germanium has 32 electrons. It's going to be 1s2, 2s2 is going to be the second orbital. 2p is going to hold 6. That's 10 electrons. 3s2, 3p6, 4s2. That's 20 electrons. We want 32. So then 3d10 is the next set. Remember, it drops down in 1. So it's 30 electrons, and now we'd want to go 4p2. So that takes care of 32 electrons. The first question says how many electrons in germanium will have the quantum number n equals 4. What we want to do is we want to look and see that the 4 is written out in front. There would be 4s2 and 4p2, so that would be a total of 4 electrons that would have that set of quantum numbers. The second question, which is a separate question, says how many electrons in germanium will have the quantum number L equals 2. And for L equals 2, the first thing we need to think about is that L equals 2 is a d orbital. So if I look at this, the only d orbital here is the 3d10. And so that would be 10 electrons having the quantum number L equals 2. There are a few groups on the periodic table that have interesting electron configurations, and one of them is chromium. And the actual configuration for chromium is argon 4s1 3d5. And the question is, why is it that? Because if I think about it, we would originally think that it's argon 4s2 3d4 because of how many electrons it has. The trick being that there is a 4s that we would think would have 2 and a 3d which has 5 orientations would have 4 in it, each of them separating out. The idea becomes that it's actually more beneficial for one of these electrons to jump up to the 3d level from the 4s level. And what this leads to is it leads to all of the electrons being unpaired. And it leads to a half-filled set of d orbitals. And some people argue that that leads to a higher level of stability. And in some ways it does, because it's reducing the amount of electrons repelling other electrons. So you should know that chromium has that configuration, unique configuration, and then you should also know that molybdenum and tungsten, Mo and W, also have this unique configuration where one electron switches from the S to the D. Copper, silver, and gold are another set of 3 that have a unique set, so that would be groups 6 and groups 11 that both have unique configurations. The configuration for copper we would expect to be argon 4s2 3d9 because copper has 29 electrons in it. Again, though, the trick is that the actual observed configuration is Ar 4s1 3d10. And again, that has to do with the idea that if we take a look at the 3D group, that there are now 10 electrons in that. And again, people argue that a full D block is more stable. Why is a little bit complicated, even I've had a slight difficulty understanding, but it's the assumption that that's the case. So again, silver and gold can also do this. There are other elements on the periodic table that can do these unique configurations, but it can become overwhelming to try and keep track of all of them. So we're going to just look at groups 6 and 11.